Computer. Hello, and welcome to another wonderful episode of the New York City Category Theory. Today, March 11th, 2026, we have Kristaps Balodis. He's going to correct my pronunciation of his last name and his first name. And he's talking about a geometric introduction to the local Langlands program, or somewhere in that region. And he's going to start off by telling us A, where he was born, B, where he did his undergraduate, C, where he did his PhD, and where he is now. Go, take it away.
Yeah, so I was born in Winnipeg, Canada. That's where I did my undergraduate and my master's. I then moved to Calgary, Canada, to do my PhD, which is where I currently am. My defense is actually scheduled for the 16th, and it's a little up in the air about where I will be after that.
Who is your thesis advisor?
Clifton Cunningham.
Very nice.
Yeah.
Okay, take it away.
Yeah, so just want to start out by saying thank you so much for inviting me to give a talk in this seminar. And I'll just remind maybe people who weren't here a couple minutes early uh, for this talk. I'm totally happy if we get off track from the sort of main proposed thing in the abstract. So if people have questions and we end up on some random tangent about representation theory, okay, I may do some steering back on course, but I'm totally happy to have a conversation and answer some questions. So, the one of the main topics of my thesis, which sits inside the local Langlands program, is something called the p-adic Kazhdan-Lusztig hypothesis. So this is one thing I will perhaps try to explain today. And so, very roughly, it can be viewed as a statement where we have some sort of category of representations. Well, in fact, this category, I'm going to decorate it with this lambda. We'll talk about what lambda means later, but the full category of representations of some p-adic group can be decomposed into these blocks labeled by these lambdas. And there should be some sort of correspondence between this and a geometric category, which is also labeled by a lambda, of equivariant perverse sheaves on some variety. Okay, so I know maybe these are some crazy words, but we will get there in due time. In particular, one possible perspective on what the Kazhdan-Lusztig hypothesis is saying is that if one takes the Grothendieck group, the Grothendieck groups of both of these categories, they're abelian categories, so that's a thing that you can do. Then there are sort of two, maybe quote unquote, obvious choices of isomorphisms between these Grothendieck groups. And the p-adic Kazhdan-Lusztig hypothesis is roughly a statement that says these two natural choices of isomorphism are actually the same isomorphism. Why one would care about this? So before this p-adic version was dreamt
Question,
up,
we put the K in front, how much information do you lose?
quite a bit, quite a bit, because I mean, it's basically like a free group generated on the simple objects. And these are both finite groups. So, and in fact, normally, like we tensor this up, say with like Z or with the rationals or the complex numbers. So we're just viewing it as like a finite dimensional vector space.
Mhm.
So, in a certain sense, yeah, you lose a lot. In particular, because say, unlike representations of finite groups, you have higher extensions. These are not semi-simple categories. So there's all sorts of interesting ways you can glue together representations, and that information is completely gone. And yet, despite the fact that this is such a maybe destructive statement, and undoubtedly there are, less um, there may be statements that people are working towards that aren't so coarse as just, oh, there's some nice isomorphism of Grothendieck groups. Which so there's people working on like categorical local Langlands. That would be something that's a much stronger statement that throws away less information. Nonetheless, one of the so the my thesis is basically comprised of two papers, and the second one is about is a paper I wrote with some collaborators where we obtain some consequences of the p-adic Kazhdan-Lusztig hypothesis. We're actually able to prove a bunch of things in representation theory in cases that we know that the Kazhdan-Lusztig hypothesis holds. So yes, you lose a lot, and yet somehow we're still able to prove a lot of things with it.
And
And in
you're
fact,
saying the hypothesis
this
holds when those two isomorphisms are equal?
sorry.
You're saying the hypothesis holds when those two isomorphisms are equal?
Yes. Yes. Yeah. A more well, I'm hoping maybe we'll be able to talk about this later, but this is more usually stated as you take a pairing, you can write down two pairings between these growth and D groups. So one, basically, it says that the simple objects over in this other growth and D group can be labeled in terms of the simple objects in the representation growth and D group. And so there's one way of writing down a pairing um, where you say, okay, the simple objects are going to be paired in such a way that this is just the Kronecker delta function. And then there's a second way of writing down a pairing, which it'll take me some time to explain what the notation means there, which is also simply you just take two other kinds of objects. You also say I'm going to define this in terms of some Kronecker delta, and then the Kazhdan-Lusztig hypothesis. There's various equivalent versions. One way that say appears in the work of Vogan is that these two pairings are equivalent or define literally the same pairing. So not like equivalent, but like, yeah, if you were to take pairing number two and evaluate it and evaluate the simple objects with respect to pairing number two, then it would return the same result as pairing number one. On the
Thank
left.
you.
If you left off the K, it's just way too hard. Is that the point? So this is a way of making it easier?
Yeah, I mean, if you leave off
Or
the
is it
K,
known to
now,
be false if you leave off the K?
well, I mean, if you leave off the K, then these are just categories. These are categories. So I don't know what it would mean to like have a pairing between the categories. Certainly the categories aren't equivalent in general. They're not equivalent in general. There is some stuff going on. There are some like other phenomenon that is present. So one of my academic siblings, James Steele, his PhD thesis was on something called Koszul duality. And he showed in certain cases that these categories are Koszul to each other. I don't fully understand the definition, but there is some sort of correspondence going on there. And then again, these categorical local Langlands people, they're working on some sort of derived level, and they're able to embed one category in the other, but it's a sort of a much more complicated version of this picture. Like for one, they don't work lambda by lambda. I know I haven't explained what those lambda are yet, but they don't work lambda, but they have a sort of more holistic perspective. And
Forget about the pairing. I mean, are there two different leave out the K's? Are there two different isomorphisms between them? Between these two?
Certainly, because like again, if you're just viewing these as if you're just viewing these as say finite dimensional vector spaces, then you've got a whole GLN's worth of isomorphisms between them.
Mhm.
No, but you said they're not equivalent as just categories. You said they're not equivalent as categories, right?
They're not equivalent as categories. They're not equivalent as categories, but there's sort of meaningful isomorphisms between the growth and D groups. Yeah.
They're not equivalent because one of them is much larger. Is representation an embedding into it? It's just not.
When will it define the objects?
You can
I'm
define the objects first.
yeah, yeah. Yeah. So I'll just say I'll start moving over to the representation theory soon, but I'll say uh I'm not sure there's an obvious reason why one category why they're not equivalent. I can't think of sort of the obvious example at the moment. But I will say in one case there's so I a lot of things I'm going to say from this point on are going to be approximately true. So there should be big asterisks on everything. But for example, there's like one very special block of this category, and the categorical local Langlands people, they embed the derived category of this category. They do find some embedding into some, I'm going to say, geometric category. It's not exactly this, but somehow this should be viewed as some sort of piece of the puzzle, some sort of localization. So um, I guess this suggests maybe the geometric category is larger in a certain sense, but now I'm really speaking out of my depth here. This is outside of the things that I work on.
And way beyond any of us here in the room.
Right.
Okay. So we're all on the same page then. Yeah. So let's talk a little bit about the representation theory side of these things. So, a representation in general of some group is just a homomorphism from that group into the invertible linear transformations on some vector space. So for us, we're going to be interested in groups that are essentially matrix groups over the p-adic numbers. And in fact, for this talk, I'll primarily just focus on GLN. So GLN, but your matrices have values in the field QP. Of course, other examples would be SON, but you put your matrices are valued in the p-adic numbers, SP2N, sort of all the, familiar kind of matrix groups.
So is V also going to be a p-adic vector space, or it could be over some other field?
No. So there is a whole industry that discusses when it's a p-adic vector space. For us, we're going to be taking V over the complex numbers. We're going to be taking it over the complex numbers. The theory doesn't change so much, if I understand correctly, if you took it to be over the L-adic numbers for L not equal to P. Because basically, in both of these cases, for complex and L not equal to P, the topologies are just not compatible at all. So any sort of topological meaningful stuff just sort of goes out the window. Suddenly, though, once L is equal to P, now you have compatible topologies, and now you're going to be talking about more interesting things about continuous maps, and the theory changes quite a bit. So, but for us, we're going to be working over the complex numbers. Now, there is still something to say of the topology. Generally, the representations that we will consider are said to be smooth. So, of course, there's no sort of differentiability going on here in the p-adic world. What we mean by this is that for every vector in the vector space, the stabilizer, so maybe I should say, the stabilizer with respect to the action given by pi, the stabilizer of that vector is an open subgroup. An open subgroup of G. So another way we say that these are they're locally constant.
Right.
We're also going to
use the word smooth, but it only requires a topology.
Yes, yeah. So we use the word smooth, even though, yeah, you shouldn't think about any sort of differential phenomenon going in. I guess part of the reason is so one is sort of interested in you might look at a given group and you'll range over all the P, including when P equals infinity, we call that the real numbers. And so we sort of want a holistic theory. Like there's a lot of statements we can make where we say, oh, let this be a smooth representation of GLN QP. And here we're imagining, oh, P is a finite prime or
Mhm.
QP is the real numbers. And of course, once you're doing the real numbers, now you really do want smooth in terms of like, oh, there's actual differentiability and stuff
Mhm.
going on there. So I guess maybe that's some of why the terminology here is smooth. It just we define it to be this because this is the thing that works, and then it gives us a uniform terminology, I suppose.
Mhm.
But I could be saying really uh, I don't know if historically that's
Well,
where
I have
that
no
came.
problem accepting this terminology. I just want to make sure I understood it correctly.
Yeah, yeah, yeah. Yeah. So the other thing I'll mention, I'll probably drop this. It isn't strictly necessary, but some statements I'm gonna make probably depend on it somewhere. One also is generally interested in admissible representations, which we ask that for any compact subgroup of G that the fixed points, the k fixed points of this vector space are finite dimensional. Um, there's a lot of stuff that, yeah, you don't need this assumption. There's maybe some things when I talk about there's some equivalences with module categories that pop up. If those statements come up, that's generally something where we want this condition.
One last clarification. So the vector space V, is that going to be finite dimensional or infinite dimensional?
Yeah, it can be infinite or finite, and yeah, I have we'll see in a moment. Yeah, well, actually, I can just make a statement now. So, suppose we want to understand the I mean, I said the main thing we'd focus on is representations of GLN QP,
Mhm.
right? So one of the simplest cases is GL1 QP, right? This is just the multiplicative group of the p-adic numbers. This is an abelian group. And so in this case, all of our irreducible representations are going to be one dimensional. So all of our irreducible representations are one dimensional in this case. Now, this will give us access to a whole bunch of one-dimensional representations of GLN, which, okay, from now on, I may not say it explicitly. I'm assuming all representations are smooth. So one thing that we can do using what we know about GLN to get what we know about GL1 to get representations of GLN is, of course, if I take an arbitrary matrix, I can take its determinant, and now I've compressed this into a single non-zero p-adic number, and I can apply then a character to that determinant. So every character of GL1 will determine simply by composing with the determinant a character of GLN-QP. Now, what's sort of perhaps surprising, there's a theorem that says all of the finite dimensional representations of GLN are exactly these ones, given by composing the determinant of the characters. So that's sort of the only interesting, in some sense, finite dimensional representation. Well, I shouldn't say that. I mean, non-irreducible ones can have a lot of interesting structure as well. But as soon as you've exhausted all the characters, boom, now we're forced to considering infinite dimensional representations.
Can I ask
Um,
about
and
can I ask about the topology on QP? So QP, I don't know much about the p-adic numbers, but I remember the p-adic numbers, you have a metric, and then
yeah,
that's how you define the topology, right?
yeah,
And then is
yeah.
it contractible?
Um, well, it's like it's totally disconnected.
Okay, so it's like a
It's
mess. So
totally,
then GLN QP is also a
Yeah.
mess then,
Yeah,
right?
intuitively, they
yeah,
look like
yeah,
Cantor sets.
Okay,
These
thank you.
yeah,
QPs in the topology look like Cantor sets.
yeah,
Gotcha.
yeah.
Thank you.
It's a really weirdo topology. Yeah, definitely. I mean, let me tell you, this is one of my this is such a shocking statement, and I feel like there's some sort of Buddhist statement for meditation here. It's that in the p-adic numbers, so take an epsilon ball, of any radius around some p-adic numbers x. Choose a random point in that epsilon ball, and it turns out that the epsilon ball of radius, or the epsilon ball about x, is equal to the epsilon ball about y. So every point of a ball is the center.
Right.
Very strange.
Yeah,
Very
it's a
strange.
non-Archimedean norm. It behaves weirdly.
Yeah, yeah.
I'll
I
watch this
absolutely.
movie.
This might be a very obscure reference, but there's a movie called I Heart Huckabees from the early 2000s, I think early 2000s, and in it there's a character that hires some existential detectives to help him with his philosophical problems, and the Dustin Hoffman's character says something like, "The universe is a sphere whose radius is nowhere and whose center
Oh,
is
yes.
everywhere."
Yep.
And I love it because that exactly describes this fact about p-adic numbers.
All
Yeah.
right. So once you figure out the Langlands program might help this poor guy.
Aha. Yes. Yes. Yeah. There's philosophical applications for solving the Langlands program. Yeah. Yeah. Okay. So I just mentioned GLN has all of these sort of all of these infinite dimensional representations. How can we possibly access them? Well, it turns out we can still leverage things that we know about GL1. And the idea.
Another question.
Yep.
Is there a classification of the characters, or can you give any examples?
Oh, yes. Yes. So there's a yes, a great classification of the characters. So if we look at the multiplicative group of the p-adic numbers, this is isomorphic to the group generated by p inverse times the multiplicative group of the p-adic integers. So maybe I should just say a little bit about what p-adic integers look like. So every single, oh, I see there's something in chat here.
It says the quote of Hoffman's character
Oh.
comes from Nicholas of Cusa in the 15th century, and it's
Oh,
Andre.
I'm actually writing that down. I'm gonna look that up.
Welcome,
I'm gonna look
Andre.
that up.
Great to hear you.
Yeah. Yeah, thanks for letting me know. Yeah. So the p-adic integers include all the integers. So basically you just take an integer and you write it out in its base p expansion. But it also includes everything of the form, so a naught plus a1 p plus a2 p2 plus dot dot dot, and so we have infinite series. So this is what a p-adic integer looks like, and sort of just like our base 10 expansions, each of these AI are between 0 and p minus 1. So the copy of the literal integers is just any of those things where the sum ends up being finite. And you might say, well, gosh, doesn't this thing diverge? Because we're taking higher and higher powers of p. Well, no, because we're using the p-adic norm, which says that the norm of p to the n is p to the minus n. So being very divisible by p means that you're small in the p-adic topology. So this is actually a convergent series. And what is the difference between this and the full field of p-adic numbers? Well, for the full field of p-adic numbers, you just now allow, maybe I should make a little more room here. You just allow finitely many exponents going off to the left. So dot 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 up to some finite term here.
Right.
So
but where this is opposite from C is now that when you go in the decimal direction, they actually get bigger.
yes, exactly. Yeah. So these terms here are big. Oh, I guess I should write minus n here if I'm taking n to be positive. Yeah. So that's why as a group, this is just generated by you take a p-adic integer and you just hit it with some finite number of powers of p inverse. And so a very important class of characters, you take a bit of a number theoretic digression, I guess, to talk about, are the characters which are trivial on this, which, by the way, which are trivial on the multiplicative group of p-adic integers, which, by the way, is a maximal compact subgroup. I don't know if that's a very meaningful thing, but if people have seen some representation theory before, oftentimes this is a strategy of like, okay, my group is not compact, but I could look at the biggest compact thing there, and that maybe somehow controls the representations of the larger group.
Well, like if
So,
you're dealing in or with ordinary complex surreal numbers, for example, inside of GLN, I would have something like the rotation group ON is compact.
exactly, exactly. Yeah, yeah, exactly. So, the unramified characters are defined exactly by exactly asking that they're trivial on the maximal compact, and then the only thing there is for you to decide how this character is going to behave is you just have to tell me where it's going to send uh, p to the -1. And so the unramified character determined by a complex number s is just going to be defined to sending p inverse to p to the s. A more slick way of defining this is to just consider the character. It's just the p-adic norm to the power of s. And so these define all of the unramified characters. And these are sort of I guess central importance to us.
Sorry, Kristaps.
Um,
Just to repeat so that I'm understanding. Unramified ones are the ones that are trivial on the maximal compact. So the ramified ones are the ones that are non-trivial on that maximal compact.
yes, exactly. And so, for example, to tell you what some ramified characters look like is so the group of uh, uh, so I hope I'm not saying this wrong, but if you take the multiplicative group here and you mod out by taking say p to the n times everything in the multiplicative group, this should be isomorphic to the integers mod p to the n. And so now you can obtain ramified characters by taking a character of this finite group, you pull it back to and then you pull it back along the quotient map, and so those will give you ramified characters. Yeah, yeah. Okay, so how can we try and use these? So to go back to this realization, this claim. Okay, there should be swaths of interesting examples of infinite dimensional representations of GLN QP. We need to talk about probably one of the most important functors in every kind of representation theory, and that's the induction functor. So if I have a group and a group G, a subgroup H, and I have some representation, say pi comma v, so pi is the vector space, pi is the action, I'm going to define the induced representation on V to be the space, the vector space of all functions from my group to the vector space, with the property that if I were to multiply by an element of H on the left, that my function should have this invariance property where that would be the same thing as if I just applied my function to X. And then remember, the output of that is a vector. And so I can apply pi of H to that vector. And so this is the definition of the induction functor. It's in general a functor from the category of representations of H to the category of representations of G.
I think it's a Kahn extension.
Uh, that very well may be. I'm not sure. I'm not sure, but that very well may be. Yeah. Um, and now in our scenario, of course, there's a couple other niceness words we need to tack on. I'm not going to mention all of them. Of course, one is we want our functions to be smooth or locally constant. So there's, a couple other things that we're going to add in. We're also in the p-adic world, we're going to restrict ourselves to the case of what is called Levy subgroups. So to explain that, and this sort of it gives rise to us using induction in two different ways. One, in the sense this is called the induction functor, but in another sense, by which we're going to take knowledge of GL1 in stages. So GL1 tells us stuff about GL2, and then those will tell us about GL3. So a Levy subgroup of GLN is just a subgroup where you take block diagonal matrices. So this will be GL, say N1 QP, right? You just put some N1 by N1 invertible matrix here. You put a block of size N2 by N2 and dot, dot, dot down to some NR, where of course N1 plus dot, dot, dot up to NR is equal to N, right? So hopefully this seems like this is a very reasonable class of subgroups because we want to study a bigger GLN. We look at subgroups that are stitched, they're just products. So I guess I should say this is, isomorphic to just the product of these smaller GLNs, right? So makes sense. We want to induce representations from here. Now, unfortunately, the story gets just a tiny bit weirder. I suppose I should tell you, though I should tell you these details. There's only so many things I should be sweeping under the rug. We also take what's called the unipotent factor or the unipotent radical. And so that is, we look at the group. So call this factor U, call this factor maybe L for Levy, where now we put the identity matrix, the corresponding identity matrices down the diagonal. Everything below the diagonal is 0, and everything above the diagonal is whatever you want, basically, because you have all these identity matrices. You don't have to worry about invertibility. These subgroups, so if you look at the subgroup generated by putting L on the left and U on the right, which happens to be a semi-direct product of L and U, this is called a parabolic subgroup.
So meant to generalize the usual terminology from the SL2 case.
Yes, exactly. And this is, I mean, of course, I'm speaking in terms of GLN everywhere here, but of course, all of these definitions, generalize to a much wider class of p-adic groups, and all of these same constructions. So thinking about subgroups of levies, this all sort of generalizes and is like very important in the general theory. Yeah. So in particular, what we're going to be interested in is parabolic induction. So this involves, now we're going to take a representation of some Levy subgroup. We're also going to make a choice of parabolic that contains it. And the definition's almost the same. Again, we're making some topological considerations. And now we do something that's maybe a little bit weird. So I know I can factor this as an L and a U. So if I write L, u x. This will factor as pi L f x. We basically just forget about the parabolic thing. So I know it's kind of weird. We do this stuff to include the parabolic, and then we forget about it. There is some justification to it. We do this, and then there's one other little thing. There's a little number that we put out in front. I don't want to worry too much about it. I'll just tell you that it's there. Basically, it's this fudge factor. If you know something about Haar measures and left and right invariance of Haar measures, translating between that. Okay, it's some normalization factor. You don't actually have to bake this into the definition, but then some of your formulas later, they get awkward. So it's important, but not. But the main takeaway is it's more or less you copy what you do for, say, finite groups, and then things generalize a little bit from there. By the way, I'll mention for the ordinary induction functor, there's also a way of going from the opposite direction, right? If I had a representation from G on G, and I take some subgroup, I can just restrict pi to H, and now I get a representation of H. And these two functors are actually adjoint to each other. I always forget which one's on the left and which one's on the right because there's different versions that get swapped around. But there's something interesting I want to show you. I wonder as category theorists, have you seen something like this before? So there's another functor going in the opposite direction. It's a little more sophisticated, but again, just think of it essentially as a restriction. This is called the Jacquet functor. It's essentially, and again, it's adjoint. But not only is it adjoint, there's this very interesting thing. So the Jacquet, so let's say Jacquet, I'll just label it with the parabolic.
Is this co-induction? Or is this...
I always get confused about which one should be induction and which ones. No, because co-induction would take you still from the smaller group to the larger group, right?
Right.
So, but something like that is about to appear.
Okay.
So I described for you this parabolic, right? There's also the opposite parabolic where you keep the Levy factor the same, but you simply swap which side of the diagonal are all zeros.
Yeah.
And it turns out that induction, if you do it this way, now Jacquet appears on the right, but with respect to the opposite parabolic. And so that induction is the ordinary induction on the opposite parabolic. And so over here we get it loops around. And so you get this sort of cycle of length 4 of these inductions. And it's a very weird this is a result that's essentially, it's called Bernstein's second adjointness theorem. And I don't know, I've never seen something like this anywhere else, where you have sort of these 4 functors that make this circular loop of a junction. So I wonder, being a category theory seminar, if people have seen this sort of phenomenon in other places. I'm curious.
I've never seen that. It loop around like that. That's really interesting.
Yeah.
Can I just say, in terms of con extensions, okay? The usual induction is left adjoint to the restriction functor. In other words, given G, you could always find, given a representation on G, you could always find a representation on a smaller h. And that functor is left adjoint to the co-induction functor.
Right. Yeah.
Okay. So no, that's not related to this, but there is that three-way thing.
Yeah.
Usual.
Well, there is kind of some relation here, because because I mean, part of why this is true is you can view it, if you go over. So Maybe this is a little
Oh, so it's off the beaten track. So, you have to use the word Langland at the end of by the end of the speech. Otherwise,
oh, okay. Okay. Yeah, yeah, yeah.
we're
So
not going to
maybe
pay you.
yeah. Oh no. Oh no.
No,
Okay.
no,
Better work
you earned
harder
your
then.
keep on
Better
this
believe
page.
us. Um okay, so at least one thing about Langlands is coming up. So um the so there's a sort of so how do we so okay, this induction we can take representations of certain subgroups, we can push it up to find larger groups. And this sort of breaks the representations of G into a dichotomy. So basically, those that appear in inductions and those that don't. So what's called a supercuspidal representation of G is essentially defined is rho, which does not appear in any induced induced representation.
So,
So
two questions.
it does.
Just wanted to
Sorry.
note the word cusp comes from the fact that, in modular forms, we're dealing with SO to Z representations. They have what they call their cusp forms or cusps.
Yeah, I'm a little confused by that actually because
Mhm.
so there is this notion of cusp form, and there is this generalizes to a notion of cuspidal automorphic form, and
Mhm.
then one would think that then the local components of that should all be cuspidal,
Mhm.
but that's simply not true.
Okay.
So to be honest, I'm actually a little confused as to why these things are called cuspidal. I'm not sure
Mm.
it's actually directly related to cuspidal modular
Okay.
forms.
Sure.
Uh,
Okay, thanks.
What's the M on the bottom? You were writing H for the subgroup. Now,
oh,
what's this M?
sorry. I oftentimes write M for the Levy subgroup. I should really be writing M let's say L for a Levy factor together with a choice of parabolic. So in this case, I mean it does not appear in the parabolic induction. Yeah. It does not it appear in the parabolic induction from any Levy subgroup. But it's also the case that
So that's like a maximality thing that it doesn't come from anywhere else.
yes, exactly. So somehow those are the representations of G that are sort of like indigenous to G. Like they can't be probed from anything smaller. And
Mhm.
there's a whole industry out there, which I'm largely ignorant of because so certain things I'm going to say in a moment, I sort of black box what happens in the supercuspidal world, and and I take that and run with it. And so one of the other things is that it turns out that every irreducible representation of G, however, does embed in the parabolic induction of something which is so sigma in this case is a supercuspidal um, of the Levy subgroup. The Levy subgroup itself has Levy subgroup. So somehow uh um yeah. So the idea is that basically, we have this divide and conquer technique. There's mathematicians out there who go and study how do we produce supercuspidal representations in general. And then there's those mathematicians who say, okay, suppose we've sorted out the supercuspidal representations. Now let's go about taking that as for granted and constructing all other irreducible representations based off of that. And we can even make a slightly more refined statement, which is so here's part one of me saying Langlands, although this isn't the Langlands conjectures yet. So it's the Langlands classification theorem. And we get even more precise information, which says for all irreducible representation, so some notation that gets used sometimes, we'll do a capital pi of G to mean the set of all irreducible representations of G. For all irreducible representations, I can find a an irreducible representation of some Levy factor such that, so I'll say there's some other conditions, we can call it tempered. It's okay to be accurate. I need to throw that in there. Let's not worry about it. It's just some, even more special case of an irreducible representation, such that pi is the unique irreducible quotient of this parabolic induction. And again, there's some sort of twisting of a character that has to happen in front. It is important, but again, it's some normalization thing. The more important takeaway from this is that the classification says every irreducible representation it can be realized as the quotient of some sort of special parabolic induction. So now we know, in fact, it's more refined than this. It appears in a supercuspal representation. We're saying, it's the quotient and it's the unique irreducible quotient. So we know exactly how it's showing up in this representation. And
this has a feel of saying that there's no cuspidal. In other words, if it's coming from a smaller one, pi is coming from a smaller one.
So the thing that's hidden in here is that G is a Levy subgroup of itself. And so for the cuspidals, like the induction from G to G is just the representation itself. And so for the supercuspidals, those are exactly the ones. Actually, those aren't exactly the ones where G is G. There's a little more subtlety going on here, but roughly speaking, this does include the case where you're not you don't show up in an induction from anything smaller.
Okay.
Yeah. And so this choice of Levy, parabolic, and representation is unique. Maybe I'll put in quotation marks again. There's some slight subtleties about that. But so this essentially allows us to talk about the standard representation. So given a pi, this induced thing that has pi as its unique quotient is what I'll call S sub pi. And now you may recognize this is, in fact, the same S sub pi that occurs at the beginning of my talk. So I've now described the sort of both objects for both pairings on the representation theoretic side. And we have very little time to talk about the geometry, but I think I can say something about that.
We're not in a rush.
Okay. Well,
Yeah.
so I wanted to ask, I mean, it's the time was until 3:30. Is that correct?
Right.
But is that
right.
normally because the talk is an hour and then conversation is like and questions are 30 minutes?
Well, our attention deficit disorder kicks in at about three.
Another option which I and others have taken there was to come back another day and do more.
Right. You may
Sure,
want to give
I
a
would-
second vote.
I would certainly be happy to do that. Yeah.
Okay. We can talk about that later. But meanwhile, go on. This is fascinating.
Okay. So then perhaps I won't since that's on the table, I won't rush so directly to the geometry because there is a little bit more to say about the representation theory.
Yeah.
So the thing is these S sub pi, these standard representations as we call them, those themselves won't necessarily be, like, in general, they're not going to be irreducible. And yes, we know that the sort of the irreducible representation it's capturing shows up as the quotient. But we may be interested to know what are the other irreducibles that show up in there. Like this is some indecomposable
Let
representation
me
with
just
pi
ask
as a
you
quotient.
one. Okay, we've been talking about a lot about irreducible. So I'm wondering, are these things semi-simple? They reduce all into irreducibles, or are they not, but you only look at the irreducibles?
Yeah, so there it's definitely not semi-simple. It's definitely not semi-simple.
Mhm.
So each of these standard representations are actually indecomposable. They do not split up into
Mhm.
sums of their simple objects at all. And there is so yes, it's definitely very interesting to ask exactly how are these representations
Okay.
glued together. Um, question number one, but before we ask though, I guess is how is it glued together? Is first we have to know what are the bits
Sure.
that appear in there. So what are the irreducibles that we're gluing together to
But
get this thing?
but that nicely motivates what you were saying about taking the quotient, that yes, you really are losing all that gluing information in the process,
Yes.
which is why it's not what's an interesting thing to look at, the full thing.
Yes, exactly, exactly. And in fact, we don't know a lot about Ext groups of representations of p-adic groups. I mean, there's certainly theorems out there about them and whatnot, but um I've really only seen like cases where we're able to actually compute like so X1 should classify the all of the extensions between say two irreducible representations. Um, it seems that there's a lot of cases where we simply don't know. Like I know of one paper that in a very special family of cases tells us exactly how to compute this. And beyond that paper, I don't know of any results that have would actually allow. So even let me say like even in the case there's a case already of GL4 that is of interest to me where we have this family, and this is one I plan to talk about perhaps in the follow-up talk. It's just got three irreducibles in it. We know what all of these sort of composition factors are going to be like with the corresponding how many times these show up in all of the standard representations. But in terms of which extension is which and how many extensions are there, I don't know. I've tried doing the computations using the few tricks we know, and it just sort of seems unwieldily already at
Mhm.
GL4. So it's interesting, and there's unexplored, interesting unexplored territory for here, around here for sure. Yeah, yeah. Um, okay, so uh, in particular, it turns out so GL1, this is about as small as things get. So so far it has no basically everything's supercuspidal, sort of vacuously because there's no Levy subgroups to restrict to. And this extends also, by the way, if you take just a product of GL1s. If you take a product of GL1s. And so, a case that is of great interest, both for just because, in some sense, it's one of the simplest kind of cases that we can deal with, but also I'll mention the representations I'm about to describe are sort of the ones that are most frequent in the global Langlands program. So those that show up as factors of some automorphic representation, if any of those words mean anything, is we take what's called the torus. So this is just the minimal Levy subgroup, right? I'm just going to take, x1 dot dot dot. It's just diagonal n by n matrices sitting in GLN. And I'm going to take as a character the character of the torus. How am I going to define it? Well, it's just going to be the product of unramified characters. So we ended up talking about those unramified characters earlier. So you're just going to take a separate complex number, S1 up to Sn, for each of those entries, take the p-adic absolute value, multiply them all together. And so the sort of very important family of representations are the representations that appear in this parabolic induction from the torus. We give the parabolic that contains it a special name, B instead of P. We call it the Borel. And we induce this character. And so there's a special class of representations. It's exactly those representations that show up in here. In fact, it turns out that the entire category of representations breaks up as a big direct sum according to equivalence classes of pairs m comma sigma. So I know we're almost just at one here. I'll maybe finish up with the last bit. I'm almost at the end of the representation theory, which would be a natural place to pause and then go to the geometry and the Langlands correspondence in the second half. So it breaks up as this direct sum of categories, where here two pairs m and let's say n are said to be equivalent if n is the result of this pair is simply the result of conjugating both of these conjugating these representations and then possibly tensoring by an unramified character. And so the representations I just described that show up in these inductions, this is what's called the principal block. So this is the part of the category that corresponds to the torus and the trivial representation of the torus, right? Because remember, we're allowed not only to conjugate, but we're allowed to twist by unramified representations, right? So that's exactly what I'm doing, is taking inductions of essentially these twists by unramified representation. So this is known as the principal block. Obviously, that notation, that choice of name should tell you that this is, in some sense, the most important block, though by no means are the other blocks to be done away with. So I guess maybe that is where I will leave it here for today, because the sort of next thing to say is to move over to the Langlands correspondence and the geometry. And so we'll focus on that case with the principal block next time. Although, of course, in the discussion to follow, I'm happy to talk more about any of this stuff.
Okay. Thank you. So next week we don't have a talk. If you want to give the second part next week, or you want to wait till the end of the semester.
The end of semester might be better. Just that way I don't have to have someone cover for my lecture for a second
Perfect.
week.
Okay, so then we'll talk about it. We'll talk about it later. First of all, any questions? Any questions from the audience?
Ask about, sort of a homework thing, if you could give a reference for some of this material you talked about today.
Oh, yeah. So a great reference is,
And you could maybe also post it when we put it on YouTube. You could post it in a comment too.
Yeah, I can. Well, I don't know where it seems to be hard to track down it seems I remember it being hard to track down this document, and so but I would be happy to
Mhm.
like send an email with it as an
Sure.
attachment. So it's called something like the local Langlands correspondence
Mm-hmm.
um, by Kudla.
Uh-huh. Yeah, I would certainly appreciate getting a copy of that if you can.
So spell his last name.
Kudla, Stephen Kudla at the University of Toronto. I think the p-adic or
Mhm.
maybe he might actually say the word non-Archimedean in the title.
Mm-hmm. Sure.
Yeah, so this is really great article. I will caution he there's these things that are essentially standard representations, but I'm not sure he
Mm-hmm.
quite calls them as such. There's sort of it turns out
Mm-hmm.
with GLN life is even sort of simpler. These can all be described by very combinatorial gadgets. So he uses a slightly different terminology there,
Or those
but
commutator gadgets, anything like the tableau you'd use if you were doing ordinary representation over real complexes,
uh
like GLNs or
kind
something
of.
different.
So there are these things called multi-segments.
Mm-hmm.
So they're not exactly like Tableau, but there
Mm-hmm.
actually are relationships between them, and in fact, there's even
Mm-hmm.
surprising things. Um, there's even surprising things by which there are ways to go between representations of
Mm-hmm.
GLNQP
Oh,
and GLNC, and of course
oh,
there's there's this there's this sure there's this sure vile duality where there's some sort of way to you build this correspondence between representations of SN and how they're labeled by
right,
Tableau and GLN,
right.
and then I mean there's a surprising thing that
So
there's
the
actually some
so the GLN
functions.
sort of has some like a vial group also, you're saying. Is I
Yes,
see.
yeah. Yeah.
Interesting.
And in fact, that's actually so the when I mentioned the Langlands classification theorem, I mentioned that these triples
Mm.
are quote unquote unique. What they're actually unique up to is conjugation by the Weyl group.
Aha.
Conjugation by the
Now, to
Weyl.
this paper you mentioned also, it does say a few words about this vial group here, the reference you were giving us.
I don't know if Kudla talks about the
Okay.
Weyl group. Um,
Okay. Yeah,
He
don't
might
worry if
he
it
might
does.
say something about it there. He might say something about it there. It is just as for GLNC, the Weyl
Mhm.
group of GLNQP is isomorphic to the symmetric group, and again,
Okay.
it's just given by the permutation matrices.
Mm-hmm.
Yeah,
Okay.
yeah.
That's interesting. No. So, I mean, the other diagram I think are also Dinkin diagrams, which also can go between discrete groups and Lie groups.
Yes,
Be also
yes.
giving like a Dinkin diagrams and roots or any of that picture whole goes over for the p-adic case or not.
Yeah, I haven't seen people discuss like the root diagrams in particular. Like,
Mm-hmm.
there's sort of these interesting ways you can like color root diagrams in the real world, in the real
Mm-hmm.
picture to get like the forms of the real
Yeah.
group. But absolutely, all of these p-adic groups. So the whole theory of root systems
Mm-hmm.
works entirely the same like for algebraic groups in general. So you have some group um, defined over a field. There's an algebraic way to define the Lie algebra.
Mm-hmm.
It decomposes as this sort of torus and this sum
Mm-hmm.
of weight spaces.
Mm-hmm.
Um, and in fact, this is maybe something I can talk about a bit next time. This is actually very, very important because each of these p-adic groups um, comes with you take the corresponding root system, you take the opposite root system, and then you
Mm-hmm.
take the
Hmm.
complex group corresponding to it called the Langlands dual. And so for GLN, its dual is just GLNC because it's a self-dual root system. But for instance, SO2n, 2n plus 1, gets swapped with SP, and vice versa. And so this is a very important thing. It's called the Langlands dual group, and it's a very important piece of the puzzle of defining what's called the Langlands L group, which is basically just that semi-direct the Galois group of your p-adic field. But now we're getting pretty out there. But
Right.
yeah, so it's absolutely essential
Okay.
that we have this technology. Yeah.
Okay, because this time you were talking, more about the other classical approach to representing groups, which is to build them up using induced representations.
Mm-hmm. Mm-hmm.
I mean, today,
Okay.
but there is the other.
Any other questions?
I have a question.
Oh, please,
Can you go
Emilio.
up to the top, from the very top of the talk? So you have this variety on the other side. Could you say a quick word on how you create that variety?
Yes, and we're in the perfect place to do it. So, I mentioned I want to talk about the representations in the principal block, right? Which is this this parabolic induction of these characters. So this is S1 dot 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 times up to Sn. So here's how we create the variety. You let lambda, and so by the way, this is that lambda, that decoration I talked about at the very beginning. You let this be the diagonal matrix, which is just on the diagonal p to the power of each of these complex numbers, and that's exactly realized in this complex dual group. And the variety v lambda is nothing else than, so you look at all n by n matrices, which are in the eigenspace, the p eigenspace under conjugation by lambda. So in particular, the varieties themselves are kind of dull. They're just all c to the n because it's a vector space. Where things get interesting, there's a group that acts on it that breaks it up into orbits, and it makes it much more interesting. So two examples I'll cover next time is, say, take the diagonal matrix p1 half, p minus 1 half. In this case, v lambda ends up being just all of those upper triangular matrices as x ranges over the complex numbers. The second example is just, you look at a slightly different example. You say, okay, that was interesting. Let's double up. What is it for if you have p1 half, p1 half, p minus 1 half, p minus 1 half? Well, it looks almost entirely the same, except now x is just a 2 by 2 complex matrix. So now this is a block diagonal matrix, for example. So that's how the varieties are produced.
So I'm a little confused. So wait, they're always just CN?
They're always just CN, even for other groups, groups.
And then the perverse sheaves on just CN is giving you all this information.
Yes, but the crucial thing is those are perverse sheaves they're equivariant. So there's some group.
Oh, it's on the quotient.
Well, not on the quotient. Well, I guess it depends on your definition of
So
equivariant.
equivariant with respect to this group you showed us of the v lambdas? Or
Sorry, you're asking how the group is
well, you said
constructed?
equivariant, so equivariant with respect to what group? Or
Yeah. So the group, say again, I'm specializing to the GLN case, so it's all those things in GLN, which now commute with lambda.
okay.
And so, for example, in this case, this is just invertible diagonal matrices, and we always act by conjugation. In this case, maybe I'll use a different color here. In this case, it's invertible block diagonal matrices. again, acting by
Right.
conjugation. And so where the interesting thing comes up is the perverse sheaves that we're getting we're taking an orbit, an equivariant local system on that orbit, and then we're taking the intersection cohomology complex between those things. And in some sense, where the interesting geometry shows up is that these orbits are their closures are usually singular. And somehow that's what's giving us interesting geometry. It's not
So
the full variety.
the stratification is what's giving you interesting geometry.
Yes, 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 yes. Yeah,
Gotcha. Okay, that makes a lot more sense. Thank you.
yeah, yeah, yeah.
Okay. Any more questions? Otherwise, we
I
thank.
have one.
Oh, sorry. Please go.
Oh, sorry about that. Yeah, so I wanted to ask you, Kristaps. Um, so right, so parabolic induction and the Jacob functor, you can define them for any algebraic group, right?
Yes.
Uh, but
Well,
Bernstein's adjointness functor, well, without the quasimodular character, but
uh-huh.
Bernstein's theorem is only for p-adic groups, right? It's not general, or is it general?
Oh, well, I mean, yeah, I guess you have to be careful what you mean by parabolic induction, right? Because for everything I've said here, I'm imagining these are p-adic groups. And so again, I buried some stuff under the rug, right? I said there's some topological considerations that I'm skipping out on, such as like smooth functions. There's some sort of compact support condition that I swept under the rug as well. And now you can do this in other cases. So, an algebraic group over the real numbers, there's also a notion about parabolic induction, but there smooth actually means smooth. And again, there's more technical things you have to be careful of. So, yeah, so anytime I've said parabolic induction or Jacquet here, I'm thinking this is specifically in the context of a p-adic group. And yeah, I don't know if Bernstein's like I'm not sure if Bernstein's second adjointness theorem, for example, holds for parabolic induction of real groups. I have no idea, but I've never heard of such a thing. Yeah.
I see. Thank
Yeah.
you.
Okay. Let's thank the speaker again. So next week we're not meeting, okay, but on the 25th we are. Morgan Rogers is going to speak about ultra rings. Everybody's invited. Let me just read the subtitle: A Categorical Approach to Unifying Boolean and Algebraic Descriptive Complexity. Anyways, it should be very interesting. Anyways, thank you very much. Thank you.
Yeah, thanks again for having me, and I look forward to coming back.
Right, so we'll do part 2 at the end of the semester. So send me an email. Okay, thank you. Take care,
Sounds good.
everybody.
Please
Okay,
pass on
take
the
care.
reference when you get a
Oh,
chance.
when you have a chance.
Yeah,
pass on the
I'll
reference.
send it right away.
Okay.
And the collaboration.
And the collaboration link, so I know how to do that.